so this is part 2 of section 1.4, continuity and one-sided limits. And in this part of the video, I'm just going to talk about one-sided limits, and I have a definition for you. So the limit from the right, and this is really about notation. This is read, the limit is x goes to c, and it's got the little plus mark up here. You just read that from the right. So the limit is x goes to c from the right of f of x equals L. Is a limit from the right, whereas the limit from the left is the limit as x goes to c with a negative exponent, and you read that the limit as x goes to c from the left of f of x equals L, and that's the limit from the left. Okay, so let's try one of these problems. So we've got evaluate the limit as x goes to 5, see a little negative, that means from the left of the square root of 5 minus x. Now I'm going to go ahead and tell you, if I just asked for the limit as x goes to 5 of the square root of 5 minus x, I would have to say it does not exist. Why? Well, you can't plug in numbers bigger than 5. You would get the square root of a negative number, right? If you plug in 6, you can't do it. So this problem can only be asked the limit as x goes to 5 from the left, because you have to plug in numbers 5 or smaller into this function. Now, we have a property back in section 1.3. It's the composition theorem that says if the inside function has a rule for taking the limit, and that's just not without the square root now, that is just a linear equation, and you're allowed to plug the 5 directly in. Now this is a composite function because of the square root part. But we have a property that says if you can take the limit of each of these by just plugging in the number, that you can do that. In other words, we just need to plug the number into this function. But keep in mind, you're only doing this from the left because this function is only defined for numbers 5 and less. That's it. So it's as simple as just plugging 5 in, the square root of 5 minus 5. But the idea is more complicated than that, because I want you to realize this function is not defined for values bigger than 5. It's only defined for values 5 and less. So we had to ask this question this way. Had to. So this down here is the answer to this question. Now this one, remember, if I put a 5 and I don't put a left or a right, that's both sides, and one side doesn't exist, and so that's why I had to put does not exist for this problem only. Okay, but down here below is that one. I don't want to confuse you. Then I've got an example C for you. Here's the one-sided limits again. I just shrunk up the definition, that's all. But we're supposed to evaluate the limit as x goes to 4 from the right, because of the plus, of the square root of x minus 2 divided by x minus 4. Okay? Now, the first thing you might want to try is just substituting 4 directly in. So let's do that. You may already see through that. We've got the limit is x. Well, actually, I don't need to write the limit again, because I'm just going to try direct substitution. That's what that's called. So direct substitution. That's what we're trying. So this is going to equal the square root of 4 minus 2 divided by 4 minus 4. So this results in numerator of 2 minus 2, denominator of 4 minus 4, which is just a big fat 0, right? 2 minus 2 is 0, over 4 minus 4 is 0. Now we know 0 divided by 0 is 0, but remember, I want you to have an alarm that goes off in your head. When you're taking limits and you see 0 over 0, what that is screaming loudly is that this function can be simplified. This is one of those problems that you can simplify this function and write a function that's equivalent to this function at everywhere but one point. Do you remember how to do that for this problem? So let me show you. So we've got the limit as x approaches 4 from the right of the square root of x minus 2 divided by x minus 4. Now the idea when you have a square root like this is to multiply by the conjugate of the factor that has the square root in it. So what is the conjugate of the square root of x minus 2? It's the square root of x plus 2. Now, I can't just do that in the numerator. I have to multiply it in the denominator as well. Remember, that's called a unity fraction. This is just equivalent to 1. So really, I'm not changing the value of my function. Now, if I simplify this, it's going to agree all at one point, but it has to simplify. So now let's keep going. This is the limit as x goes to 4 from the right. Now I multiply the square root of x times the square root of x. So that equals square root of x sub square root of x is square root of x squared, which is x. Square root of x times 2 is positive 2 square root of x. Negative 2 times square root of x is minus 2 square root of x. And negative 2 times positive 2 is minus 4. Now in the denominator, okay, we've got, here's the deal. When you do this on the other side, okay, in the numerator you have to multiply it out. The whole reason we did the conjugate is so this would happen. But in the denominator, you often don't need to distribute. Let's just leave it as 2 separate factors for now. You probably already see why. Because this is the limit as x approaches 4 from the right still of, now x minus 4 is all that's left in the numerator, over x minus 4 times the square root of x plus 2. The x minus 4's cancel. Now what we have here is we're taking the limit as x goes to 4 from the right of a different function. This function matches the original function except at one point, at the one that canceled out. At x equals 4, because I set that equal to 0, it differs. So this you're allowed to plug in 4, whereas the original function up here you're not allowed to substitute in 4. Now, we have a theorem that says if a function differs from another function all but one point, you are allowed to use that new function to take your limit. So the question is, can we substitute 4 directly in here? And we can. That would be 1 over the square root of 4 plus 2, which is going to be 1 over 2 plus 2, which is 1/4. And there's something I want you to think about this problem. You know, it said the limit of x goes to 4 from the right. So we're talking about plugging numbers in larger than 4, but getting closer and closer and closer to 4. But since this simplified and it turned into a function that I can directly substitute the 4 in, I didn't have to consider the left and the right. So keep in mind the left and the right doesn't really matter if you can plug the number directly in to the function. In other words, the function is defined at that point. Now this one was not defined at that point, yet I found a function that was defined the same as the original function except at that one point. And we have a theorem that says it is okay to plug directly into that. Which brings me to the next problem. Now I want you to notice the difference. Look, that looks exactly the same, but it's the limit as x goes to 4 from the left of that function. Now, I'm not going to do this again because remember what I said on the last problem, it came down to the point where when it was time to consider the left or the right, we plugged the number directly in and we got 1/4. So this is not going to turn out any differently. The answer for the very same reasons, is going to be 1/4. Okay, if you take a look at the graph, the limit from the left and the limit from the right match in this graph. Now there's a hole in the graph though. So this is a removable discontinuity at x equals 4. If you pull this up in Desmos and graph it, you won't see the hole, but the hole is really there because you're not allowed to plug in 4 as it is. But again, back here, we found a function that was identical to this function except at one point, and that's what I have over here, well, down here. Let me highlight it. That function is right here, which is equivalent to the one circled in yellow except at 4. So it doesn't matter if we come from the left or the right on this particular function because we were allowed to plug the value directly in. Okay? Alright, so we have a theorem here, and what this theorem, excuse my sliding around, there we go. What this theorem says is, theorem 1.1, let f be a function and let c and l be real numbers, because they always are. The limit of f of x as x approaches c is L if and only if, by the way, if you start using if and only if a lot in your theorems, you could just see IFF, that means if and only if. It means you read it in both directions. So basically, if the limit as x goes to c of f of x equals L, and the limit as x goes to c, I didn't say from the left, or did I? Anyway, that's from the left, and the limit as x goes to c of f of x equals L, that's the limit from the right. If the left and the right give you the same values, then you can say the limit exists. Okay? And it's L. The if and only if means you could read it the other way. If the limit from the left and the limit from the right, that means the function has a limit. Okay? So this says discuss continuity on a closed interval. So I don't have a problem for theorem 1.10 right now, but I want to talk about continuity on a closed interval. So it says a function f is continuous on the closed interval ab when f is continuous on the open interval ab and the limit as x goes to a from the right of f of x equals f of a. In other words, the limit value is the same as the function value at the endpoint a. So a is on the left side. And notice the limit as x goes to b from the left of f of x equals f of b. So again, the limit value equals the function value. Now, if you see this in action, xy axis right here, okay, and a continuous function, that's continuous, you agree, here's a and here's b. What they're saying is you can include these endpoints for continuity as long as, now watch this one on the left, it says if you approach A from the right, that's this way. If we get closer and closer to A from the right, and the limit value is the same as the function value, and this one says if you approach B from the left, the limit value, and here's f of b up here, the limit value is the same as the function value, then you can say you're continuous on a closed interval. So that's what's happening there. Now let's try to do that in a problem. Let's address it specifically in an example. I may end up erasing this graph down here. We might need the space. But here we go. It says discuss continuity on the closed interval, -3 to 3. That's our interval. Now, is this function, first of all, you have to ask yourself, is this continuous on the open interval? And we've already done that kind of work. So continuous on the open interval first. And so to find that, I have to ask myself, is this undefined anywhere? Are there any values you cannot plug into this function? Well, you can't have a negative under a square root, right? Okay, what kind of numbers would we plug in for t to give us a negative under a square root? Well, anything bigger than 3 is going to be a problem, right? Because 9 minus 3 squared is 9 minus 9 is 0. That's okay. But if you plug in, say, 4, that'd be 9 minus 4 squared is 16. 9 minus 16 is a negative number. You see what I mean? So, and the same thing in -3. So what we know is you're okay between -3 and 3, right? You're allowed to plug in any numbers you want between -3 and 3. You could even plug in -3 and +3, but we're looking at the open interval right now. So the first thing you do is look at the open interval. And it's continuous everywhere because there's nowhere between -3 and 3 that this function is undefined. Okay? Now let's check the endpoints. So to check the endpoints, I'm going to do this all in different colors. First I'm going to do it black. If we take the limit as x approaches, now what is the left-hand endpoint? That's your a value, it's -3. So the limit as x approaches -3 from the right of our function, 3 minus the square root of 9 minus 3 squared. Oh, don't plug in, I'm sorry, 9 minus t squared. That's our function. Okay, now the question is, how do you evaluate this limit? Well, if you can just do this problem by direct substitution, in other words, it doesn't cause you any issues, then you're allowed to do that. So if we plug it right in, 3 minus the square root of 9 minus 3 squared, that gives us 3 minus the square root of 0, right? Which is 3. That's my limit value. It's also my function value, because if I just take Well, I didn't do negative 3. Stand by. Still get the same answer. But the limit value is the same as the function value, because the function value is just taking negative 3 and plug it in. So we handled this part. Okay? Now on the other side, if we take the limit as x approaches, now what's b is our right endpoint from the left of 3 minus the square root of 9 minus t squared. Again, is it okay to plug 3 directly in there? So 3 minus the square root of 9 minus 3 squared is 3 minus square root of 0, which is 3. Now, again, my question to you is the limit value, which is 3, the same as the function value? Is that the same answer as just taking 3 and plug it in? Well, yes, that's actually how we got it. So now I have checked the right endpoint. So first of all, you check the open interval and make sure it's continuous on the open interval. Then to check the left endpoint, you take the limit as x goes to the left value from the right. And then you take the limit as x goes to the right value from the left. How more confusing can you be? And this is why I drew this picture over here, to make that more clear for you. All right, and here's a really good theorem. It's going to be super helpful, this theorem. It's going to be without proof, okay, but that's okay. So we got theorem 1.11, properties of continuity. It says if b is a real number and f and g are continuous at x equals c. So we've got 2 continuous functions and b is just some old real number. Then the functions listed below are also continuous. So a scalar multiple. So if we want to take a continuous function and just multiply it by a number like 5, then it's still going to be a continuous function. Or if you add 2 continuous functions together, you get a brand new continuous function. You can also subtract them, notice the plus or minus. Or if you would like to multiply 2 continuous functions together, that means you get a brand new continuous function. That's pretty powerful to think about that. And then divide. If you wanted to divide 2 continuous functions, you get a brand new continuous function as long as, now here's the deal here, that denominator is not equal to 0. So if you take an x value, we'll call it c, and plug it into the denominator, as long as that's not 0, then you have a brand new continuous function. And that's been a lot of the focus in this section, right, is where is the denominator 0, because that's where the function is undefined. So that makes perfectly good sense. Here's another part of that theorem, functions that are continuous at every point in their domain, okay? So polynomial functions are continuous. Not only are they continuous at every point in their domain, but look, they're continuous from negative infinity to infinity, which is pretty cool. A polynomial is defined everywhere and continuous everywhere. Now, rational functions, that's not true. Rational functions are continuous everywhere in their domain, which means, if you know what a rational function is, like 1 over x minus 2, but it's not continuous at x equals 2, right? But x equals 2 is not in the domain. It is continuous everywhere else. So you just got to figure out where the denominator is equal to 0. That's not in the domain. It's continuous everywhere else. A radical function, for example, x plus 4. Now that's not continuous everywhere, but it's continuous everywhere in its domain, okay? What's the domain of this? Well, you can only plug in numbers greater than or equal to negative 4, right? If you plug in like negative 5, it gives you the square root of a negative number. We can't have that. We would get imaginary numbers. So its domain is negative 4, but as long as you are talking about numbers negative 4 and larger, this thing is continuous, okay? As a matter of fact, y'all know what that looks like. That is a square root function shifted left 4 units, so it looks like that. And trigonometric functions, y'all know them well, right? Sine of x, cosine of x, tangent of x, secant of x, cosecant of x, and cotangent of x. Those things are continuous at every point in their domain. So, for example, for sine of x, the domain is all real numbers, so it's continuous on all real numbers. And you can picture it. It looks like that forever, right? That thing is definitely continuous on the whole real number line. Cosine of x is similar. It's continuous on the whole real number line because it's defined on the whole real number line. And it's got no holes, jumps, or breaks. Those are pretty, don't you think? And then the other 4 guys now, you got to be careful. They're continuous on their domain, but those things are not continuous everywhere. So, for example, tangent of x, you remember what that looks like? It's got vertical asymptotes at the pi over 2's. So it's continuous between negative pi over 2 and positive pi over 2. And then again between pi over 2 and like 3 pi over 2. But not over the whole real number line. And you can make similar arguments for secant and cosecant. They're not continuous everywhere, but they're continuous everywhere in their domain. In other words, the numbers you're allowed to substitute into the function. Okay, here's another very helpful theorem. Theorem 1.12, continuity of a composite function. It says if g is continuous at c and f is continuous at g of c, then the composite function f composite g of x or f of g of x is continuous at c. All right, let's break that down with an example. I think that's going to make more sense. So it says if g is continuous at c and f is continuous at g of c. Okay, so the inside function, it says if g, that's the inside function, is continuous at c. So the question is g of x equal x to the third continuous at c? Then you might ask, what's c? It doesn't matter. Where is g of x equals x to the third continuous? Everywhere. It's a polynomial. So to answer that question, it's yes, because it's a polynomial, right? Now here's the next thing. So if g is continuous at c and f is continuous at g of c, okay? Now, I don't have a c value, but g of c is c to the third. If I take c to the third and plug it in to that function, do I get a continuous function? Well, this is continuous also. 5x plus 1 is another polynomial. Okay, so I can say that the composition f of g of x, which is really just 5x to the third plus 1, is continuous. Really, could just plug it in and say, hey, it's a polynomial, so it's continuous too. So you didn't necessarily have to use this theorem. So another way to think about it, let's look at another one, continuity of h of x. So first you got to look at the inside function, okay? So is x minus 1 continuous? Fact is, yes, it's continuous on the whole real number line because it's a polynomial. Okay, but now is 1 over the square root of x minus 1 continuous? Well, no, because the problem is right here, if you have the square root of x equal to 0, it's not continuous, but we're plugging in the x minus 1, so basically at x equals 1, it's not continuous. If that makes sense. I'm having a hard time addressing the way this is saying it. To me, it's easier, and I think you're going to find it the same thing, just to go ahead and do the composition. Plug it in and see if you have a continuous function. We don't here because there was a place where the denominator equals to 0. So that's probably the safest way to handle it. You're using the theorem to do that, but it's confusing to address it, I think, exactly the way the theorem reads. But that's all you're doing when you plug it in. So here we go. Determine intervals on which f is continuous. So we're trying to write the interval the function's continuous. So instead of saying, this is just a different way of asking the same question. Instead of saying it's not continuous at x equals 5, we would say it's continuous from negative infinity to 5 and then union 5 to infinity. See what I mean? So we're writing in interval notation instead of just saying x can't be 5. My question to you here is, what can x be? Okay. So first of all, let's look at the domain of our functions. X cannot be 0, right? Why? Because it would make the denominator 0. But it's got one more offender, right? X has to be also greater than 0. Why in the world? Because you can't take the square root of negative numbers, right? And not get a real answer anyway. And we're searching for real answers when you're dealing in calculus. So really, x, and this jumps into here, this is our issue. As long as x is greater than 0, we have a continuous function, okay? But if x is equal to 0 or it's some number less than 0, It's an undefined function, therefore it is not continuous there. So how do I write that in interval notation? With a parenthesis to infinity. So that answers the question. The interval, it's continuous, is between 0 and infinity. What about cosine of 1 over x? So these are composition functions, okay, or composite functions. Now, we know cosine, just by itself, cosine of theta, let's just say, is continuous everywhere. Remember I had that crazy looking graph? The bottom one. You know what that wave graph looks like. The sine graph just shifted is cosine. Okay, so cosine's continuous everywhere. But now I got something plugged in, my inside function, okay, my g of x, if I use the theorem, is not continuous everywhere. What's the problem with 1 over x? Well, x can't be 0, right? So that's the problem. This is not continuous at x equals 0, because if it were 0, it would be cosine of 1 over 0, which is cosine of an undefined, and we can't do that. But what can we plug in there? Anything else you want to. Okay, 0 is the only problem. So how do I write that in interval notation? Well, if you think about the real number line and you take 0 out, here's 0, it can't be that, but it can be all of this and all of this. That means we're going to have a continuous function from negative infinity to 0 with a parenthesis, because we're leaving it out, union 0 to infinity. Okay? Okay, I have the intermediate value theorem here. I'm going to try to do it as quickly as I can because my computer says I'm about to run out of time to video. So, it says if f is continuous, very important, that part required, on a closed interval AB, that means the endpoints are included, and f of A is not equal to f of B, and k is any number between f of A and f of B, then there's at least one number c in AB such that f of c equals k. Okay, so first of all, let's set this up in a picture form. So f is continuous on AB. So let's just draw something. There you go. That's continuous, right? And it says f of A is not equal to f of B. So here's f of A. If I plug A into the function, there's f of A. Okay. I plug B into the function, here's f of B up here. Now it goes on to say k is any number between f of A and f of B. So k is a y value, right? So k is any number in here, doesn't matter where you put it, as long as it's between f of A and f of B. It says as long as your function is continuous, there is at least one number c in AB. So that means this next value down here, such that f of c equals k. How do you find it? You work backwards. Okay? And then there we go. And there's your c value. Now, if your function, my red line, is not continuous, you can't say that's true. If your function is not continuous, let's do something like this, and then pick up right here, okay? Not continuous, you agree? So, here is A, so f of A is right here, okay? F of B, here's B, f of B is right here. Well, let's pick a K, okay? K, let's say K is right here. Then I go back to my function and try to get the c value back. I can't do it, right? I go back to my function and I can't find it. There's nothing there because it's not a continuous function. So this is pretty powerful, this intermediate value theorem. Okay, so you know if you have a continuous function that you can always trace your x value back when you have a k between f of A and f of B. Okay, this is my last intended problem. We'll see if I can get it done in a minute and 5 seconds. It says explain why the function has a 0 in the given interval. Okay, so you have these endpoints. What we want to use is the intermediate value theorem. I'm going to abbreviate. Okay, now what the intermediate value theorem says is if f of A is not equal to f of B. So let's check that first. What's the f of A? So that's f of 0. F of 0 is 0 to the third. Plus 5 times 0 minus 3, that equals negative 3. What's f of B? Well, what's B? Is 1, right? So that's 1 to the third plus 5 times 1 minus 3. That's going to be 1 plus 5 is 6 minus 3 is 3. So we've done the first thing. We showed that the endpoints do not match. So f of A is not equal to f of B. The next question is this function continuous? And you say, yes, 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 yes. Why? Because it's a polynomial, right? Okay, so I was in the middle of working on this problem, and the video timed out so this is what we had done. I don't even know when it shut off. So I'm going to go slowly and explain. We're using the intermediate value theorem. And there's three things that you have to do when you're using the intermediate value theorem. The first thing that you have to do is you have to check that f of a is not equal to f of b. So, first of all, what is a and b in this problem? So a is 0 and b is 1. So to find out if f of a is not equal to f of b, I just took those values and substituted in. So I did f of 0, which gave me 0 to the third, plus 5 times 0 minus 3, which is negative 3. And then I calculated f of b. B is 1, so I've got 1 to the third plus 5 times 1 minus 3. That gave me 6 minus 3 is 3. And clearly, negative 3 is not equal to positive 3, so f of a is not equal to f of b. The next thing, and really honestly, you might want to check this first. Because if you don't have a continuous function on that interval that they gave us, you don't even have to check f of a and f of b. Of course, if f of a is not equal to f of b, you don't have to check if it's continuous. So whichever you'd like to check first. But how do I know this is a continuous function? Well, it's a polynomial, and that's what's written here. I know it's hard to decipher, but yes, this is a polynomial. Therefore, it's continuous not only on 0 to 1, but this thing's continuous between negative infinity and infinity. So it's definitely continuous on 0 to 1. Now, check out the directions. They want to say, explain why the function has a 0 on the given interval. Now, remind me, what is a 0? Well, you know what a 0 is. A 0 is when f of some number equals 0. And this guy right here is the 0. Okay, so whatever number you plug into the function gives you an answer of 0. That's called a 0 of the function. Now, let's think about this graph-wise. Okay, I'm not going to draw the graph of this thing, although y'all kind of know what this looks like, right? X to the third, you know what it looks like. One side's up, the other side's pointing down. But anyway, now here's what we do know. When I plug in 0, so when we plugged in the endpoint 0, we got an answer of negative 3. So 0, and then I'm going to do this in red. My answer was negative 3. And then when we plug in 1, so here's 1, we got an answer of positive 3. Okay, so when I plug in 1, and when we mark in my black or gray, I get an answer of positive 3. Right? So far, so good. That's what I found out. And then how do I use the idea of it's continuous? Well, if it's continuous, it has to go from y equals negative 3 to y equals positive 3 with no holes, jumps, or breaks in the graph. Therefore, we are assured that there is a 0. Now, I'm not saying it's right here, but I know there's a 0 between 0 and 1 by the intermediate value theorem. So basically, since this was less than 0, and then f of 1 was greater than 0, as long as one's negative and one's positive, and you have a continuous function, it has to cross the x-axis. It has to have 0. Hopefully that makes sense, and I hope you have a great day.